All right, good day, everybody. 4.7 applications involving exponential functions. Okay, so now we're looking at word problems with regards to exponential functions. Okay, so we're going to go through 3 examples here. One with regards to, financing or interest. Then we're going to go through one with regards to growth or doubling. And then we're going to go through one which is called half-life. Okay. So we learned over the days that our base function is y equals b to the power x for an exponential function. So b was your base, okay, which we learned. And now we're adding something here, which is your a value. So it's a little bit different than what we've been doing with regards to stretch and compresses. But this a is now considered our initial value or initial amount. Then the b is your base, but in this case, it's going to be our growth or decay factor. So what we're growing by or what we're decaying by. And then the x in the exponent is going to be time. Okay, so let's look at our first example. An antique vase was purchased in the year 2000 for $8,000. If the vase or vase appreciates in value, appreciate meaning go up, as opposed to depreciate, which means goes down. So it goes up in value by 6% a year. What is the estimated value in the year 2040 to the nearest cent? Okay, so when we do money questions, we're going to have our y or f of x equals our initial value. And then when we're doing percentage, when it's going up 6%, we have to add that 6% to 100% because it's 100% plus 6%. Okay, so 1% as a decimal is just 1. And if it's going up, we're going to add the 6%. But we can never use this 6% as it is. We have to convert it to a decimal. So to convert from a percentage to a decimal, we divide by 100. When you divide by 100, you get 0.06. And then x, or the exponent, is going to be our years. So I should put our a value here. So a is our initial value. So our initial value was the 8,000 that we purchased it for. Now it's going to go up by 6%, so it's 100% plus 6%. But as decimals, it's 1 plus 0.06. And then the exponent is our years. So we bought it in year 2000, and we want to know what the value is at 40 years later. So we're going to put 40 here for time. And now we just evaluate. So 8,000 times 1.06 to the power of 40. So make sure you do the power first. So 1.06 to the power of 40 equals, and then we're going to multiply that answer by 8,000. And we get 82, holy moly, that's a lot of, so we get $82,285.74. Okay, this is a 3, so this stays as a 4. So I double check that one more time. That seems like a lot. 1.06 to the power of 40 times 8,000. Yeah, that's the answer. Okay, so that vase, which started at $8,000, going up by 6% a year, is now worth $82,000. Okay, now we're getting to doubling. So doubling is when the base is 2. Okay, anytime we're talking about doubling, our base, our b value, is going to be 2. Okay, so f of x, which is our y, is going to equal our a, which is our initial value. The base is always going to be 2 when you're doubling. Okay, because it's 100% plus 100%, which is 1 plus 1, and that gives you 2. But then your exponent's a little bit different. So this is the time. So we had here, it was just the time, which was 40. But now we're going to divide by d, which represents doubling time, or double time. So it means how long it takes to double. And then t is your time in years. Okay, so it says here when the base of exponent relation is 2, that's this. That relation is described as doubling. Example of formula that could be used to determine the population after time, t, so time is t, where d is the doubling time. So t is time, d is doubling time. And a is the initial value or population in this case. Okay, so a bacterial culture begins with 7,500 bacteria. The bacteria doubles its population every 36 hours. How many bacteria are present after 36 hours? Okay, so we start y equals our initial value or population is 7,500. We are doing double since it says doubles. We're using 2 as our base. Okay, our time we want to know is after 36 hours, and our double time is 36. Okay, so it's end up canceling out to be 1. So 36 divided by 36 is just 1. So we get 2 times 7,500, which is 15,000. Okay, these aren't always going to cancel out. A lot of times this number in the top will be larger. So you just divide it, and then you do 2 to the power of whatever that answer is. Okay. B, how many bacteria are present after 144 hours? So y equals 7,500. 2 is our doubling. And now this represents t, because 144 hours have passed. But every 36 hours, it doubles. Okay, so 7,500 times 2. Now we divide these. We divide them, we get 4. So 2 to the power of 4 is 16, and then 16 times 7,500. And we get the answer of 120,000. Okay, these are word problems, so you should be putting a therefore statement at the end. So like for the first one, we should say after 40 years, the vase is now worth that much of money. Likewise, these ones, after 36 hours, the population is such. And again, the population of the bacteria is 120,000 after 144 hours. Okay, last example now. So we had double time or doubling, and now we have half-life. So anytime you see half-life, the base is now a half. Okay, so we did a double is 2, half is half. Okay, so if you read through it, the base of exponent is half, describing half-life, determining the remaining mass of a decaying substance after t, with time is t. And now the only difference between doubling and half-life besides the base is this letter here. So before it was a D, for doubling, H is now half-life. Half-life. Okay, so H is the half-life, and A again is the initial amount or initial mass. Okay, number 1. In a laboratory, a sample of iodine has a half-life of 8 days. The initial sample is 320. How much remains after 4 days? So y equals, our initial amount is 320 times, you could put 0.5, it's fine, instead of a half. Since it's a real life question, it's okay to use decimals. T is 4, okay, that's our time, and we divide it by the half-life, which is 8. So 320 times 0.05, 4 over 8 is 0.5. Okay, now we're going to plug that into the formula. sorry, in a calculator, 0.5 to the power of 0.5 equals, and we times that answer by 320, and we get 226.27 milligrams remains. Okay, so initial sample is 320. After 4 days, 226 milligrams remains. You can obviously think about half-life or like decay. For example, it would be if you left a water in a glass and you left it on your counter, slowly the water will decrease in the glass, okay, because it's evaporating. Okay, so think about that. So when you have a substance, it's decaying or it's decreasing over time. Okay, so I always think about water in a glass, it evaporates, so that amount of water decreases. Okay, and our last one here, how much remains after 24 days? So again, y equals 320, we have half-life, our time is 24 now, and our half-life is still 8. So 24 divided by 8 is 3. So again, punch it into our calculator, 0.5 to the power of 3 equals, and multiply that by 320. So we get 40. So after 24 days, we have 40 milligrams remaining of the iodine 131. Okay, we don't have the homework at the bottom here. So on my screen again, like we did previously, page 261, 1 to 10, 12, and 15. But let me just double check if that's everything I want you guys to do. 261. They're all pretty quick questions. So 1 through 10. Actually, you could take out number 12. So 1 to 10 and 15. So take out question 12. Let me see. Yeah, that's good. Okay, so again, homework, page 261, 1 to 10, and 15. Okay, I hope everything is doing well, and we'll see you tomorrow.